right, we're here with Trishul. Tell us a little bit about yourself.
Okay, so I'm a researcher in Microsoft Research. I've been there for around 15 years now. My background is in high-performance computing, making computers more efficient. Most recently, I spent the last 2 years in Bing, building a scalable web search engine from scratch. So that was very exciting. It got me hooked on distributed systems. And something that's relevant is I really got into computers because of my love for AI. And I was seduced by AI in the 80s. And then I was very disillusioned when I realized that AI at that point was just smoke and mirrors and clever programming. And so I went off and started working on making computers more powerful.
And when you got started, what was the first computer that you used?
So my first computer was a Commodore 64.
All right.
And, I did all the peeks and pokes.
Yeah.
And actually, the second programming language I taught myself was Lisp because I was in love with AI.
Yeah. And so your background's in high-performance computing, distributed systems, and how did you get back into AI at Microsoft?
Yeah, so that's one of the wonderful things about Microsoft Research, in the sense that you have this incredible critical mass of experts in all areas. So I came back, I knew I wanted to work on distributed systems, and that was the point where deep learning was in the air. And I looked at the literature there and I said, I can build a better distributed system for training deep learning systems. And I looked around, but I didn't know much about deep learning. Mm-hmm. So John Platt, who's a machine learning expert, Leon Botou, who's an expert on scalable algorithms for training machine learning systems, they're at Microsoft. Yeah. I just looked up who the experts were, and then they turned out to be at MSR. So I took a crash course in machine learning from these guys. John Platt, actually for the last 2 years, he met with me every day, once a week. And so I learned an incredible amount from him. And discussions from leading people, Patrice Simard. I think MSR is the only place I could have done this.
Yeah. And how many people are on your team?
So it's a team of 4 people. And I told Harry Shum this, and he said that his predecessor at Bing, Ken Moss, had told him that you need 4 people to change the world.
Yeah.
3 is too little, and 5 is too many. So it was just a lucky coincidence, I guess.
So tell us about Project Atom.
Okay. So Project Atom is an effort to build a scalable, large-scale distributed system for training deep neural nets purely from commodity PCs. And it's much more scalable and efficient than existing systems. And we've used it to train a model that does image recognition, large-scale image recognition. It's a very large-scale task, recognizing around 22,000 different categories from an image. And we have the best performance on that task using Project Atom.
And what is a deep neural network?
So what a neural network is, first of all, is it's a computational framework for automatic pattern recognition that's inspired by what we know about biology and how the brain works. And what deep neural nets is, it adds one layer there. It's saying that you have multiple layers of these neural networks that are connected to each other. And the true magic of deep neural nets is that it turns out that this hierarchy or these layers is very important because it allows you to learn these hierarchical features. And that turns out to be key and different from kind of general neural nets. And that's where the deepness comes in.
And how do you teach a computer to see? And maybe a better way to phrase that would be, how do you teach a computer to understand what it's seeing?
That's right. So I think one way to look at it is, well, how do we learn how to see? Right? And the way we go about it is we see a lot of information around us. Our eyes are constantly taking things in. If you look at a baby, they're very curious looking around at things. And our vision system takes about 12 years to develop. And constantly we're seeing things and we get information about what we're seeing. So that someone tells us that's so-and-so, that object is so-and-so. And that's exactly how we train a computer system to see using Project Atom. We give it a lot of training data, a lot of images, and we tell it that this is a tree, or this is a king penguin, or this is a Pembroke Welsh corgi. And this is the magic of deep learning. Just with that information, a lot of training data, a lot of labels of what the information is, it automatically learns. So it automatically learns how to extract features from these images so that when you show it an image it's never seen before, it can accurately categorize it in one of the categories you already taught it to.
Do you have to train every single thing? I mean, will it think that a horse is a big dog?
No, actually it's incredibly accurate, and it turns out that you require some amount of scale. So if you give it too little training data, it doesn't learn at all. But once you hit some critical mass, if you've given sufficient training data and you have a sufficiently complicated model that can learn it, it's actually incredibly accurate at not just telling horses from dogs, but much more fine-grained classification. Like, that's not just a corgi, that's a Pembroke Welsh corgi. It's not a Cardigan Welsh corgi. And it's actually better at some of this fine-grained classification than I am.
And what are the things that it looks for?
So what it really looks for, and like this is kind of what we found out by examining the trained neural network after the fact.
Yeah.
And what we see is kind of, like it has these hierarchical features. So the lower layers of the network learn edge detectors. The higher layers of the network kind of learn things about, like textures and some kind of generic shapes. And as you go higher and higher up the network, what you find is what you learn is kind of concepts that are recognizable to us. So there are specific neurons at the top level that respond when it sees human faces. There's neurons that respond when they see images of dogs. There's neurons that respond when they see kind of text in an image. And so it automatically extracts these features that it puts together to come up with the ultimate classification for an image.
And how different is this from how a human would discern what something is as like a young child?
So we don't fully understand how the human vision system works, but actually the neural network you've trained is hugely inspired from there. And so to the best of our knowledge, like, it uses 5 or 6 layers of a type of network called convolutional neural nets. And understanding of the human visual system is that there's also about 5 or 6 levels deep of these neuron layers. And the thing about convolutional neural nets is they have this notion of local receptive fields, whereas neurons, rather than looking at the whole image, they look at just narrow portions of the image. And the higher levels of the hierarchy kind of see more and more of the image. And that's how we think that the human visual cortex is also organized. So it's remarkably similar to the extent that we understand the cortex.
So as a developer, I might think that if I was building a system like Project Atom, I might have it like look for features on a dog, like here are the eyes, here's the nose, look for floppy ears. Is that the way that you start with a system like that, or do you just start feeding it pictures and allow it to decide?
I think that's the really interesting thing about the system is that, as a programmer, you would think that's how you want to program this, right? You will train, like this is what an eye looks like, this is how the shape is, and stuff like that. And what we found out is with vision, systems like that have been done and people have worked on it, but the accuracy of those are significantly worse than system trained by Atom, which what you do is you just present images and just say this is what the image is and nothing more than that. And the deep neural network is automatically able to figure out, the features that are important for characterizing the images according to the labels you give it. And that's kind of the magic about deep neural nets we don't fully understand. But one thing that's really interesting, for a programmer to think about is you could look at the model Atom is trained as representing a program that the system has synthesized that's more complicated than any program we're able to write ourselves. So it's kind of, maybe a new paradigm of programming where you can kind of program certain sophisticated things that you couldn't in any other way just by using large amounts of training data and a system with a learning algorithm.
And once you've trained a system, is that something that you can leverage and copy to other systems, or does each one have to do its own level of training?
So that's the I think really interesting and exciting possibility with deep neural nets is once you've trained it on a large amount of diverse data, it's not task specific. The features it's learned actually transfer over to other tasks. So I can train it on task 1 and leverage that training and retrain it without losing the information I've already trained on task 2. And the interesting thing is when you train it on task 2, you can actually also improve the performance on task 1. So it's kind of additive, which is beautiful.
I've heard when Peter Lee, the head of Microsoft Research, talks about how we're training computers to speak. When we introduce a second language, like Spanish, the first language improves, and that's kind of like what you just said.
That's exactly right.
So how does that happen for vision?
So I think the way of thinking about it is, depending on the images you present to the system, it learns kind of types of features. So one thing we noticed is when we were starting to train the system is our input data set didn't have really, I think, almost any cartoon images. And so it performed very poorly on classifying cartoon images because it had never seen them, and that was kind of very alien to it.
Yeah.
And once you gave it cartoon images, not only did it get that correctly, but its performance on other images improved, because what it does is it had found certain other features that really it could only learn when it was given that domain of information, but it could kind of transfer that over.
So Project Atom uses vision. I mean, so it's one sensor.
Yes.
Are there other sensors that would come into play? Like, would you use sound and hearing?
Absolutely, I think so. So, you know, like, we definitely are looking at using it for text, for speech, but more interestingly, multimodal, combining these all of these things together. Like, you know, I've never seen the Eiffel Tower. You describe the Eiffel Tower to me, then I have a chance when I first see it that, oh yeah, that looks like the Eiffel Tower from the description. And so this transfer learning across multiple modalities is very exciting and very interesting.
So Microsoft Research has a focus on getting AI ready for everyday use. How does Project Atom, how is that useful to us?
I think the possibilities are immense, and so let me just outline a few maybe. So one thing that Peter has thought would be very useful, and I agree with him, is like you walk around with a cell phone, you take a photograph of what you're eating, and it tells you the calorie content, the nutritional value, and you might decide based on that, it's like, wow, those fries are way too, I'll eat less of them. Things like I'm just wandering in my backyard, and I might look at a plant and say, well, I'm curious, what is that? Tell me what it is. And then more future looking is like, if you could take an image of something and describe a scene, it could really help blind people. What's going on around you, just kind of describe things around it. And I think the ultimate goal is to use this to help machines understand, represent, and explain the world around us and understand us. And so putting those two things together, you could think, the ultimate goal is like, your best personal assistant that's always around with you because you carry all these devices, but now these devices know you, they know the world around you, and what can you do with that?
And is it possible for these different devices with AI to speak to each other? And
that's absolutely, I think that's the real possibility, because you can have all these different devices kind of learning on different data, and with this transfer learning I told you, and also looking at kind of combining multimodal information. So I could learn something just from images, I could learn something else from text. Can I put them together? And so these different devices can kind of talk to each other, communicate, and share learnings, I think.
And have you seen any examples of like where you've just been really impressed or surprised by something that it's recognized or understood?
Yes, there have been some like incredibly amazing things. So actually my boss, Yimin Wang, who was actually an early supporter of this project, shared with us a photo of he had taken in his backyard. And it was really a very abstract scene, grass and stuff. And there was a tiny rabbit in the corner. And he just did it jokingly to say that, I don't think any system would say that's a rabbit. And lo and behold, it got the grass and it got the rabbit, and it was pretty amazing.
Wow.
And on this, ImageNet task I've been talking about, I kind of compared my performance on it with the computers, and it was like, it blew me out of the water. So like, I'm really embarrassed about how bad I am at recognizing objects.
Thanks so much for talking to us today.
You're welcome. Thank you.